space. So this is the magnitude of the softmax in the direction of that class. Yes? Does that make sense? So if you call this the boundary where that class and that class have the same magnitude, then the more you are inside this, the more certain you are about classifying this class, and then that is the magnitude of the softmax. So the problem with softmax thresholding is that it is not trained on a background class. So you have a lot of examples from the unknown class which can have high magnitude in the direction of one of the classes, either of them. So if you just threshold the softmax, you're also getting rid of a lot of examples that should be classified, okay? And that's what so that will reduce your precision, your coverage of the actual set, okay? This is what they call the entropic open set loss. So what they show is that if this is the background class here, so this is the classification in the background class, the entropic open set, it moves all the points towards the background class, and then it keeps the magnitude low on the other softmax direction, so on the direction of the correctly classified classes. And furthermore, they add the objective sphere, which just reduces everything. So if you threshold in the objective sphere space, then you will probably be rejecting all the unknown classes, and you will still be keeping the actual classes. Okay? So those are the results. Now, how do they go about this? And they go about it by designing cost functions. So they change the cost function to train the models, so that they take into account that, well, we have to put a penalty on the entropy in the known unknowns, and then we have to put a penalty on the softmax magnitude in the known unknowns, and that way you do both things. So they go through a whole discussion on why other methods are not good, which I mean, we've seen the other methods, so maybe we don't have to go through them. But just as a full disclosure, we got all the references from here. And well, you can see the methods. So there's threshold in softmax, uncertainty estimation, open max, which they call open max the state of the art, which is a bold statement, but it's what they want to compare themselves to. And then you have the background class, which is something that we didn't see very much we didn't see at all in the series, but this is just training an extra class, so it's not that interesting. And so yeah, well, here's the information.
So you train on the background class, but the figures above.
Yes, so you use both in your training set. So your training set is d prime c and d prime b, but the difference is in the cost function that you use. The cost function does tell the difference between a background class and the normal class. Okay. So the main takeaway from figure 1, which is the motivation. Sorry that I go back and forth. So the main takeaway from figure 1, which is the motivation for the design of their losses, is that, so first, the magnitudes for unknown samples in deep future space are often lower than those for known samples. So these are usually lower than the ones for known samples. So that is one thing that you want to that we would like to include. And then that's what we're going to build into the entropic set loss function. Okay, cool. So the first equation is, and I think I will need some help here because I did not completely get how this is a loss function, but okay, so that's the entropic open set loss, which is the first loss function. If we say SC is the softmax output, so just defined as softmax output for class C. Yeah. Then the open set loss, if it is in the known training examples, then you just define the normal loss, which is normally not defined like that, but it's normally you need the classification target as well. But maybe they just omitted that. But if it is an unknown, then you average over all the softmax outputs. So what this is trying to do is is to increase the entropy in the unknown classes, okay? Because you're trying to maximize this number, and what the theorem shows, what the proof shows, is that this is maximized when all the softmax outputs are equal. So when each of the softmax outputs is 1 over c, and then of course the entropy is maximized. So this is what they call the entropic set open loss. So if you maximize this, then you will have a model that for the test samples is going to try to produce a flat softmax output. And for these ones, since you're optimizing the same loss function, for DC test, you're going to have a model that is trying to make high softmax outputs for the correct class. Okay? However, they finish the theorem that's saying that this formulation does not have a single minimum. Okay, so the thing is that you can maximize entropy in other ways, and that might lead to undesired convergence results. So how do we make this have a single minimum? And the answer to make it sure is regularizing the cost function. They call it Objectosphere, so they come up with a fancy name for it, and they call it Objectosphere loss, and they say, well, we're trying to make the model converge to the Objectosphere or something like that. In truth, it's a regularizing term that imposes a penalty, so lambda is a regularization coefficient, and then you have a term that makes this, so this controls, C controls the boundary, so it controls the margin of error, so this controls how high you want your activation to be for the known targets, so for the known classes. And on the unknowns, you're trying to minimize the softmax response. Okay? Yeah, that's the feature. So the previous to softmax activations. So you're trying to make these activations as small as possible. Okay, so it's a regularizing term. So you have your entropic loss. So you cross your entropic open set loss, and then you add a regularizing term to it, and it becomes what they call the Objectosphere loss. And what they argue is that this does have a single minimum. Yes?
Can we just go back to the chart at the top of the page, please? The difference between B and C.
Oh yeah, we're going to come to this in a bit. Yeah. So this is the other important result, but we'll get there. And then they argue that since we are using this Objectosphere loss, then it makes sense to not threshold over the softmax, but threshold over the softmax times the feature magnitude. So how do they call that? The feature response. Okay. So now you're making a threshold over this. And then they go on to the results.
So what was F again? Sorry.
F is the response prior to softmax. So you're trying to minimize the response, the activations of the network, to features that are not, so that are no.
It try to minimize feature response.
Yes, you're trying to minimize feature response.
Yeah.
So one of the other arguments that they gave is that some